Hello everyone, my name is Jill Piyush Kumar Khatiwala and I am honored to present a research titled Evaluating the Reliability of Digital Forensic Evidence Discovered by Large Language Models, a case study. This work was done in collaboration with Daniel Adai and Dr. Weifang Xu at University of Baltimore. Today, I'll take you through a journey of our research. We'll begin the context and motivation behind this work, then introduce the framework we developed. I'll walk you through how it worked step by step, share real case insights, and finally present our evaluation findings, contribution, and future direction. So let's start with introduction. So in today's world, digital evidence is everywhere, from our phones to our browsers to our chat logs, even including our smartwatch. But analyzing it is a difficult. Investigators often have to sift through the thousands of raw data manually, process that slow and error-prone. These records come from diverse platforms and tools like messaging applications, location tracker, search history, cloud backups, and system logs, and include many types of data types such as timestamp, app name, phone number, locations, and email. That's where larger language models or LLMs come in. This AI system can read and understand unstructured text, making them strong candidate to assist in extracting meaningful forensic evidence quickly at scale. But LLM aren't flawless. They can misinterpret the text, skip key details, or worse hallucinate data that isn't there. These slides show a real world where AI added a fake message, "Hey John PKG," and misread a phone number. Even we can see there is a timestamp which wasn't extracted by the AI because it's in the epoch format. That's why we can't blindly trust AI. We need method to check and validate everything is it finds. So the question, so the question is how do we make AI useful but also reliable for digital forensics? Our goal was to design system that preserves the efficiency and scale of LLMs while adding a layer of traceability and structure. We wanted every AI generated or extracted artifacts to be clearly linked to its original source record so analyst and forensic examiner can confidently interpret and validate results. That level of accountability and transparency is the motivation behind our proposed framework. Let me walk you through a core of our contribution, a forensic analysis pipeline. It starts with a forensic image of a mobile device. From there, we extract internal database like WhatsApp messages or browsing history using file signature based identification. This signature helps us to recognize and extract SQL databases and other file formats reliably, even if the file name or extension have been altered. Then we convert these database into structured CSV or the text file. Every single record is tagged with a unique identifier or UID, so we know exactly where it came from. And these UID tag record are passed into larger language model, which extract the forensic artifacts like name, timestamp, email, or app name, etc. But we don't stop there. We keep UID with extracted entity. That way, if we ever need to verify a piece of evidence, we know exactly where to look. And just to check that AI has not hallucinated or modified any of the artifacts. Then we merge all of this data into digital forensic knowledge graph. Imagine a web where each node is person, timestamp, or app event, and then edge shows how they are connected. Finally, the graph helps us to validate a relationship. Was this person really at this location before deleting a app? Did the search happen before the message? With this approach, AI doesn't replace the investigator. It helps them to see the whole picture clearly and reliably. So let's now that we have seen a full overview of the pipeline, let's break it down into its three core steps. Starting step one, UID tagging. So step one ensures traceability. Each record from device is tagged with UID built in for each row and the UID made of its file path, database, and raw number. So basically, it's a hash value of device, file path, and database name, and then the table name and row ID is included, and we can see in the green font how the actual UID look like. And then it attached with every single row of SQLite, so it will have like a unique ID for each row. In even with the database with the same name, will have a different unique ID for each row. And then let's look into the step two. So LLM scans this record and extract the meaningful entity, names, emails, search term, app identifier, and we store this alongside the UID so that every single result is traceable and greatly speed up the review process and reduce the human error. Additionally, we have saved every single category, different artifacts category into separate CSV file along with their UID. So later on, it is easier to track back and trace back to the source and also for the categorized artifact review by the investigator. So in the step three, which is validation through visualization. So we merge all the extracted data into graph, and this is done based on purely on UID. Each UID corresponds to a single source row from the original forensic database and all the artifacts extracted from that row, such as name, timestamp, phone number, or app name app name are automatically connected as a part of same subgraph. This structure reflects the logical grouping of artifacts belonging to the same data record. The logic here is straightforward. If all the extracted entities share the same UID, they must have originated from the same line of evidence and inherently linked. This UID-based linking avoids any speculative association and ensures factual consistency. Additionally, all the app names extracted from the single device are grouped together and alphabetically ordered within the graph. This preserves the device context and highlights the pattern across the apps while visually maintaining and clarity during analysis. By containing entities through shared UID, we eliminate the guesswork in the linking artifacts and preserve the accurate context. This graph allow us to detect inconsistencies such as false link or missing nodes because everything is UID tag and we can verify every single connection and ensure no fabricated relationship are introduced. So let's start with the case study. So we applied our Vault pipeline to a real Android image from a organized crime theft case, and the device belongs to one of our suspect named Heisenberg, and it contains 61 application, 13 gigabyte of data, and over 2800 forensic database. Our goal was to test our pipeline under real-world conditions. So to evaluate framework, we defined three research questions, focus on accuracy, traceability, and forensic best practices. So we use a manually reviewed forensic report as a ground truth to compare our extracted results. So let's start with the research question one. So research question one asks how can standardized framework evaluate the reliability of LLM refined forensic evidence using knowledge graph visualization? To answer this, we use four standard metrics. First, evidence extraction accuracy tell us how many artifacts of the system currently extracted out of total possible. Here it was like 40 out of 42, giving us accuracy of 95.24%. And then second matrix is forensic artifacts recall measures how many true positives were we captured compared to both true and false positive. We had like 40 true positive and 2 false positive, such which also resulted in 95.24% recall. And forensic artifacts precision evaluates the system's ability to avoid avoid false negative. In our case, there were none, giving us perfect precision of 100%. And finally, F1 score, the harmonic mean of precision and recall, help us balance both metrics. With numbers above our F1 score came out to 97.56%. So this means our pipeline is not just good at finding real evidence but also avoids including irrelevant and fake one, ensuring both accuracy and precision. Now now that we have seen how well the system performed using classic accuracy metrics in research question one, let's look deeper into how our graph-based validation help detect subtle errors. Accuracy alone doesn't reveal whether the certain relationships are falsely created or if the metadata is missing entirely. So this slide shows example of hallucinated and mislinked evidence that were exposed through our knowledge graph. This slide shows how our knowledge graph help us detect issues that may go unnoticed during a raw data review. We identified two specific type of hallucinated and mislinked evidence. So first is a fake communication link. The LLM mistakenly connected to users via fabricated email address that doesn't exist in source record. And second is missing metadata. Important context like app source or file origin was missing from extracted evidence. So these issues were flagged during graph validation. The graph made it visually obvious when certain entities didn't connect logically and lacked the supporting details. So this demonstrates that beyond our raw accuracy metrics, our system can detect the structural problem in the evidence using the contextual reasoning. Now let's talk about research question 2. So research question 2 asks how well can our system trace back each extracted artifacts to its original source, and does the graph accurately represent the relationship? So to evaluate this, we use two metrics. Uh, First, evidence traceability rate, which is measure the percentage of extracted entities that retain their UID and could be traced back to their origin. And another is knowledge graph connectivity accuracy, which we have to check check against the ground truth defined relationship and the graph results. And that we end up having 94.44% in knowledge graph connectivity accuracy. And this shows that a UID based structure is not only traceable but also preserve the contextual accuracy when visualized. Then let's talk about research question 3. So research question 3 explored whether our pipeline supports practice in digital forensic investigation. We use four quantitative criteria, but first we'll look at the equation matrix we have used, which is evidence consolidation accuracy, which uh, which check the artifacts matching expected context against the ground truth of total accepted artifacts. And in that matter, whatever the evidence was found by the AI, which was exactly 100% correct with the ground truth found evidence, which means we have evidence consolidated accuracy at 100%. And then along with this, we have used another four quantitative criteria. First, human readability, which is structure output in clean format like CSV and visual graph summary, chain of evidence, and then UI with the chain of evidence with the UID tagging and preserved data lineage from source artifacts, and then contextual completeness, and then error detection support, where the graph highlight the inconsistency and hallucinations. All four criteria were met and confirmed the framework's alignment with the forensic standard. So let's talk about the final summary of all the validation metrics we have used in our approach. So we have accuracy, precision, recall, and effort score for research question one, and then ETR and KGCS for knowledge graph for research question two, and four quantitative criteria with contextual consolidated metrics in research question three. So these are all the summary of our results for each metrics, and then we can and then in this summary, we propose a UID-based LLM pipeline that brings the traceability, structure validation, and forensic reliability to AI extracted evidence. And key contribution that from our side was a UID tagged pipeline for source verification, LLM-based extraction of digital evidence, and graph validation from contextual error detection. And for the future work, we are planning to extend this framework to cross revise correlation and integrate timeline reconstruction, support export in sticks format for securing evidence sharing, and collaborate with the law enforcement to deployment this trial on actual different type of devices and cases to train and use more better large language model and get more accurate results. So with this, I would like to thank you for your attention, and I am happy to take questions and discuss further details about our framework. Thank you.